insertion sort, this is another technique that we do the sort by create a sorted list by inserting each new element into its appropriate place in an array. So each successive element in the array to be sorted is inserted into the proper place with respect to the other already sorted elements. So if you look at the image, we have unsorted list here. We can start from the current index 0. We compare the next index. We found that this is smaller. We took that and insert to 0. We pretty much swap. Okay, like we insert to that location. Then we swap. So if you look at the algorithms here, insert elements, right? We say insertion sort start from count going from 1 to the size -1. Which insert elements get 0 to 1? Like the first one that we look at, we pass 0 and 1 in, right? 0 and 1, which is 36 and 10. Okay, so start index is 36, index is 10. Right? I mean the values. Start index, this is like 0 here, which is give you 36. And count count is 1. So that's why we have 10. Set finish to false. Set current to end index. So that means current index equals to 1, which is getting the value of 10 here, and current -1, which is 0, getting 36. 10 is less than 36, that's why we swap. So that's why we do insert, that's what they call, into the 36. We pretty much swap 10 and 36 and decrement the current. Alright, current was 1, now it's 0, right? Set more to search 2, current does not equal to start index, is 0 that equals to start index. So we pretty much just no more to search. They're done. We done. Then we go back to the loop. Now we get to the second iteration of the insertion sort loop, which we pass 0 again and 2 count, right? From 1 to size -1, so 0 to n. Let's look at, we pass 0 and 2, right? So it's going to start the same. Look at 24, right? So we see it's already swapped on the first one. So this is 24. Let's go look at the one before it. 24 and 36. Yes, we got to swap. And then it keeps, it's still in the same iteration of insert elements. Right, because there's still more to search since current does not equal to start index. Let's go back, and you see current is always decrement, so that's why now current is moving to 24 and compare with 10. Then there's no more, because swap, we don't have to swap. 10 is less than 24, and decrement, right? And current index happen to be does not equal. It happened to be equal to start index, so we're done. So we exit the loop. And we keep doing this, the same insertion sort with the next round. Right now, we have 0 to 3 in, and 6 start to compare to the previous 6 and 36. Then we insert. You see that why they call insert? Because It's actually try to insert into the sorted list already, right, in between, and keep inserting in between again until the top. Then we got the sorted list. And last one, 32, insert into the right location. And then you see that that's how when insert, it just make it sorted. So that's why we call insertion sort. So let's look at the snapshot here. We get the sorted part at the top and unsorted part at the bottom. Which is the same. We can implement it in Java here. So insert elements past start index and end index. We set the finish to false. Then we can keep looping while multisearch and not finished. Then we loop. Current start from end index because we always look at the bottom. But the bottom in this case depending on here, which is actually it's not the bottom of the list, it's just count from the increment the count from the top, but the bottom of the part that we touch sort, which is the blue portion after sorted. So multisearch, make it to true first, then it start doing this, not finished multisearch, then compare the values right at the bottom to the one before it. If it is 12, swap it and reduce the current. Then we get another loop, right, to compare the one before until no multisearch, which is current not equal to start. I mean, if it's equal to start index, yes. If it's not equal, still multisearch. So else, this one pretty much just if the values, right, current no longer less than the values before, then it's finished. So exit the loop. And insertion sort itself pretty much just activate to the list from 1 to the size, but starting index is a key that pass the 0 and the count. Now, if you look at the big O, we can see that it's just the same as selection sort and bubble sort. In general case, it's going to have big O of n square. But insertion sort has the best case. In the best case, the data are already sorted in ascending order. Insertion element is called only n times. So if it's in ascending, then it's going to cost only n times, because only one comparison is made each time and no swap are necessary, right? The reason that this is a trick here, right? Because if it's already greater than, then we done. Finish is true, right? So that make a difference. We don't have to do the whole list again. Just like the last image that we see here. We always know that the top part is always sorted, right? So because this is insertion sort, we start from the beginning. Like here, we see, hey, 32 has to go after 24. We done, we not keep doing again. That's why the trick is when it's greater than, here we said finish is true. We no longer have to do again, because multisearch is set to true too. makes true that it is false and multi-search is false already from here. So it's exit the loop. So that make the insertion sort for the best cases better than selection sort and bubble sort, because selection sort and bubble sort, like I said, is called redundant when we do insertion sort. It keeps swapping even itself. So insertion sort is better. The maximum number of comparison is made only when elements in the array are in reverse order. Now, look at n-squared sort are very time consuming for sorting large arrays. So several sorting methods that work better when n is large are presented in this section, which is called the n log n sorts. Right, the efficiency of this algorithm is achieved at the expense of the simplicity seen in the straight selection, bubble, and insertion sorts. Okay, so we look at this.